We might want to know how long it will take a computer to apply an algorithm and get a solution to an instance of a problem. To do that, we'll perform a time complexity analysis. This will give us some function f of n, where f of n is the number of steps required to solve the problem when the input size is n. But the actual time depends on how long it takes the actual computer to execute an actual instruction. And that in turn might depend on the actual instruction in the actual programming language. To avoid these complexities, we can focus on counting basic operations. A basic operation is whatever we define it to be. However, we often ignore recording a value or retrieving a value and focus on actual computations or decisions. Later on, we'll see why this actually is a reasonable thing to do. So consider our two sorting algorithms. In one, we took the first remaining element of our set and compared it with the rest, swapping it out anytime we found a smaller element. Now each comparison is a decision. Is the value we have smaller than the value we're looking at? And since it's a decision, we'd count it as a basic operation. However, when we actually swap the elements, that's a store and retrieve, so we wouldn't count these as steps. And so we found our time complexity was. Now our other sorting algorithm also had comparisons and store and retrieve operations, so it also had a time complexity of. However, there's an important difference. In the first algorithm, we had to perform every comparison every time. So regardless of the actual values, every case required this many steps. We call this an every case time complexity. And since the worst case is also a case, this is also a worst case time complexity. But for the second algorithm, some cases could be sorted in fewer steps. Only the worst case required this many steps. So this is a worst case time complexity, but since some cases can be solved in fewer steps, it's not an every case time complexity. We could go further and consider a best case scenario. Suppose our list is. The first element of our sorted list is going to be A1. Next, we take A2, and A2 is less than A1, or it isn't, but in either case we'd be able to place it after one step. This gives us a sorted list consisting of two elements, where one of these is A1 and the other is A2. Now consider A3. If A3 is less than S1, we can place it immediately. This is the best possible case. And now our list is, and we need to place A4. If A4 is less than A3, we can place it immediately, giving us the list. And clearly, the best case scenario will be when each AN is less than the preceding one, and A3 is less than whichever of A1 or A2 is smaller. Sorting this best case list will require n-1 steps, so the best case time complexity is. Generally speaking, we don't care about the best case time complexity, except when we do. We can also find the average case time complexity. To do this, we have to assume some probabilities. As this can get extremely complicated because we need to work with and assign probabilities, we won't worry about it for now. For example, let's consider the sequential search algorithm. In the worst case, we need to check all n elements of our set, requiring n steps. But in the best case, the search term is the first element of the set, requiring just one step. So the average case would require n plus 1 steps. Or does it? And the problem is averages are tricky. In this case, the average case does take n plus 1/2 steps. But again, more generally, we have to be very careful about how we work with our probabilities. So as the preceding examples show, finding the actual time complexity of an algorithm can be very tricky. To simplify the process, we'll need to introduce some more ideas. We'll take a look at those next.